So if let's say we cannot use ideal gas equation, what can be used? Okay, if let's say we cannot use ideal gas equation, another things that we can use is what we call as compressibility factor, which is a measure of deviation from ideal gas equation. Okay, so in compressibility factor, we have introduced the factor Z. Maksudnya ada Z kat sini. So instead of PV is equals to RT, we have actually PV is equals to ZRT. And Z ni, how do we calculate Z? Is the specific volume, the actual one, divided by the specific volume of ideal one, where V ideal we can determine from the ideal gas equation. Okay, V ideal ni is actually PV equals to RT. So this is considered as V ideal. So nanti kalau kita determine V actual, we know the V actual, then we can get Z volume. Okay, kalau tak, we can also determine also V actual by knowing Z volume multiply with the V ideal. Right, so this is where actually we can use this equation just to make correction to the ideal gas equation. So the further away Z is from the unity, which means the further away Z from 1, if let's say Z is equals to 1, so if you use the initial equation PV equals to ZRT, if Z equals to 1, then you will get ideal gas, which is PV equals to RT. But if let's say the real gases, for real gases where Z is beyond 1, Z is less than 1, the more gas deviate from ideal gas behavior. So for example, kalau kita dapat Z is equals to 0.5, it just shows that this is not an ideal gas behavior. So we need to use compressibility factor in order for us to determine the property of the gases. So gases behave as an ideal gas at low densities, which is at low pressure, high temperature. So the question is, what's the criteria for low pressure and high temperature? The pressure or temperature of a gas is high or low relative to its critical temperature or pressure. So maksudnya kalau dia duduk dekat critical temperature tu or critical pressure or at critical point, it is not valid for us to use ideal gas equation. So might as well we need to introduce the Z, the compressibility factor tadi. So gases behave differently at different temperature and pressure, but they behave very much at the same temperature and pressure is normalized with respect to the critical temperature and pressure. So in order for us to do the normalization, we introduce what we call as reduced pressure, PR. PR is equals to P over critical pressure. Reduced temperature, TR, is equals to T over critical temperature, and VR is the V actual divided by RT critical divided by P critical. So why this information is important? Remember, this is dimensionless. Dimensionless maksudnya tak ada unit. Okay, tak ada unit. Kan, ini KPA, ini kilopascal, cancel, tak ada unit. So reduce pressure, reduce temperature, reduce parameters ni, kita nak gunakan dia supaya we can determine the Z factor. Okay, so the Z factor for all gases is approximately the same at the same reduced pressure and temperature. This is what we call as principle of corresponding states. Okay, so tengok kat sini kalau dekat graph ni, this is actually comparison of Z factors for various gases. So if let's say you have methane is represented by X, you can see that there are lots of methane here dekat ada TR with different reduced temperature. Okay, so at reduced temperature, if you can recall balik, reduced temperature is equals to the temperature at that particular point that you want to determine the property divided by the critical temperature of that particular substance. Okay, and then you be able to get the TR. So if let's say you are operating it at reduced pressure of 3. Again, remember, reduced pressure nak calculate macam mana? Reduced pressure is equals to P, okay, divided by critical pressure. P is the pressure that you are actually looking at. Okay, so now if let's say you calculate PR, and then you wanted to know you already calculate your TR, and then you have this line. So and then you'll be able to see that okay, Z is equals to 0.8. So once you got 0.8, masukkan dalam ni, then you'll be able to, you know the pressure that you are looking at, the temperature for example, then you can calculate your volume. Okay, so this is where actually the corresponding states, principle of corresponding state, you use the compressibility factor Z can be used, and you can start to see that there will be a different reduced pressure, and for different reduced pressure dia akan ada different graph. Because for example like graph yang saya introduce kat sini, this is for low pressures. Low pressure which is 0 less than PR less than 1.0. Okay, so if let's say your reduced pressure is equals to 0.5, you can use this particular graph in order for you to determine the Z value and so on lah. But if let's say you are using a higher one, 0 less than PR less than 7, then you need to use different graph. Okay, so at a very low pressure, gases behave as an ideal gas regardless of temperature, as I mentioned earlier. Low pressure and very high temperature. Okay, at high temperature, which is temperature reduced bigger than 2, ideal gas behavior can be assumed with good accuracy regardless of pressure, and the deviation of a gas from ideal gas behavior is greatest in the vicinity of the critical point. Maksudnya kalau kita ada critical point, okay, kat sini, this is where actually the gas is not ideal. This is where memang ideal gas equation tak boleh pakai. You have to start to use compressibility factor Z. Okay. And finally, the final few slides that I would like to share with you is what we call as equation of state and exploring others. Is there any other equation beyond ideal gas equation and compressibility factor? Yes, there are. Sebab tu orang dah buat research yang banyak. There are many people who have done this particular research and they introduce different kind of equation of state. So, due to some limitation in the ideal gas equation, there are a lot more of equation of states that has been derived to provide more accurate estimation of the thermodynamic properties. Some of the things that you will go through nanti bila dah masuk second year, dah masuk next semester, you'll be able to come to this particular equation of state again and again. Even later when you learn simulation using high Cs, for example, you'll be introduced to actually this kind of property, thermodynamic property packages, which means that they are using this particular equation to determine the properties of the equation. Determine the properties of this of at certain condition. Okay, so for example, like example of equation of states, we can have van der Waals equation, Beatty-Bridgman, Benedict-Webb-Rubin, Tank-Robinson and so on. Okay, and this is just a comparison of error lah. Maksudnya kalau contohnya if let's say we are using van der Waals punya equation at higher pressure, maybe not that good. Okay, you can start to see that at lower pressure, okay, boleh pakai. Tapi bila dia dah masuk higher pressure, the error can be as much as 20.7% at low temperature. Tapi kalau kita guna Benedict-Webb-Rubin, which is at the bottom, okay, at low pressure is okay, good. And we go to a bit higher pressure, is still okay. Even at actually 20 megapascal pun not that bad lah, because it's 22.1%. Okay, so you can this is what actually we need to be clever in actually deciding what kind of equation of state that we want to use, so that we be able to determine or predict the properties of the thermodynamic properties at that particular period, at that particular point lah. Okay, so I think that's all that I would like to share with all of you. So I hope that you'll be able to enjoy the video. I hope that you could understand this. So thank you very much for your time watching this. Alright, so Assalamualaikum warahmatullahi taala wabarakatuh.